Using your amp meter. What happens inside your amp meter is you have a coil of wire all wrapped up inside that amp meter all the way around. And when you have current flowing through a piece of wire, around the outside you have magnetic lines of flux. So when you have your amp meter, which has a coil of wire going around magnetic lines of flux, it becomes all fluxed up. It becomes all fluxed up. Thank you very much. I appreciate that. So when it does that, it starts seeing that. Now what you want to do with your amp meter is try and line it up. You'll see that on the top of it you'll see a little line. You'll see a little line here, a little line here on this side, and then typically there's one down here at the bottom as well. If you put those lines right like this, it becomes a set of crosshairs. That crosshairs is where you want to have the amp wire running through there, because that's going to give you the closest. Have you noticed as you move it around you get different amp readings? Good. Put it right there in the crosshairs and you'll get your best amp reading for that particular reading. Okay, so this is the SSC Wi-Fi swivel head amp ohm meter. Does temperature, capacitance, volts, ohms, everything that's out there, and it is Wi-Fi too. So that's the newest thing that's coming out with all of our meters. All right, so let's look at that. If I had a condenser fan motor and a compressor, notice they're both wired pretty much exactly the same way on the inside. Easy. So could I get it? Are these in series or parallel? They're all in parallel. Would they receive source voltage from here to here and then to here? Yes. Would this one receive source voltage here to here to here to here? Good. So we know that they're in parallel. In this particular case, we're going to get a condenser fan reading, and we might get 3 amps on that condenser fan motor. If we took our amp meter and brought it down to here, I may see what? 12 amps? Good. So my current flow through here is 12 amps. Current flow through here was 3 amps. If I went back to a common wire between the two of them, what should I expect to see here? 15 amps. Very good, very good. So again, it's just the magnetism around the outside of the wire, which is going to be the flux that we're going to be able to pick up that amperage. Schematics are typically two types of schematics. You can have a pictorial. The pictorial is typically how it's laid out inside the system. And you're going to have ladder diagrams, which is going to be the exact same wiring diagram, but it's going to show you pretty much like rungs of a ladder, everything that's in the high voltage side and everything that's in the low voltage side of that system. Switches, they're control devices. They just either open or close to turn the voltage on or off to that unit. I wanted to say power, but that's the wrong terminology, is that right? So they'd turn the voltage on or off. They're always drawn with no voltage applied to the system. So in this case, it would be a normally closed set of contacts. This would be a normally open set of contacts. This would be a normally open set of contacts on a switch, and this would be a switch with a pole that can go in 2 directions. If I have a single pole that can go in 2 directions, that would be a single pole double throw switch. Single pole double throw switch. This would be a single pole, single throw switch. Everybody good with that? Single pole, single throw switch, single pole, double throw switch. All right. In this particular case, we have a open switch, and it would be a single pole, single throw switch. A contactor would have how many poles? 2 poles. How many directions does it make? 1. So that would be a double pole, single throw switch. Everybody good with that? Double pole. Could I have a triple pole, single throw switch? 3-phase contactor. Could I have a single pole, single throw contactor? Yes, you've seen those. Sometimes they call those as 1.5 poles, right? It's 2 different poles, but they'll just put a wire right across there. Good, we'll call it a 1.5 pole sometimes. Good. So good. You're understanding that. So inside this type of a switch, this is a, look at this up here. We've got a common going to a normally open switch, and we've got a common going to a normally closed switch. You see that? Then this one is a common going to a normally open switch, and this is a common going to a normally closed switch. And this is that coil of wire that runs down at the bottom. That's that magnet part of that switch. In this case, the 24 volts would be applied here. The switch would close, and 1 and 3 would now make, and 1 and 2 would open. 4 and 6 would make, and 4 and 5 would open. So really, what I have there is a double throw switch. Everybody seeing that? Double pull, double throw switch. Very good. All right, so this would be a single pole double throw switch, and I would have the common to a normally closed switch, and I would have the common to a normally open switch, and this would be my coil, which would turn into a magnet and pull that in. Everybody good? Sweet. Double pole, double throw, there it is. Switch is a combination of two single pole double throw switches built together in one action. The two sets of poles, double throw switches, operate independently of each other. The control circuit, typically the control circuit is what we call our 24 volt circuit. That's going to be our thermostat and anything that's in that circuit. The load circuit is typically going to be our high voltage, 120 or 240 volt side of that circuit. So our control circuit controls the loads, is that right? Good. So on this contactor, what's the difference between a contactor and a fan relay? Both of them have a magnet, both of them have contacts. All of that stuff is typically the same, but it's usually right around 20 amps. Is where they make the difference. If it goes above 20 amps, it becomes a contactor. Below 20 amps, it's a relay. Don't know why, but that's kind of what where the breakover is. So just a little piece of information for you to understand. All right, so transformers. Here's one of those things that I really like about transformers is I'm going to take in a bunch of high voltage into one side of a transformer, and then I'm going to make those magnetic lines of flux go right on over to that other side, kind of like what happens in our amp meter, is that right? So those magnetic lines of flux in here are going to jump over to this, and there's a certain ratio of windings from this side to this side that's going to turn that 240 volts into 24 volts, and it's going to be a 10-to-1 ratio. For every 10 windings on this side, it's going to be 1 winding on this side. So 240 drops down to 24. Does that make sense? Good. So we have our primary voltage, our secondary voltage, and then we have that VA rating. Is that right? VA? What is VA? What is volts times amps? Remember from Ohm's law? Volts times amps was what? Volts times amps is what? 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 Yeah, volts times amps is what? Yeah, volts times amps is watts. Absolutely. Volts times amps is watts. So when we're talking about a VA rating, we're talking about what? Watts, power. That's right. That's our power. That's our watts. So really we could say primary voltage, secondary voltage, and wattage. Is that right? Yeah, that's basically what we're looking at there. It's on a basic level. But so, how many times have you changed a transformer because it's burnt? Put the new transformer in there, and then we wait to see what? If the smoke comes out, is that right? That's how we've learned this stuff. Plug it in, wait for the smoke to come out. If the smoke comes out, it doesn't work anymore. Is that right? Oh, wow. Wouldn't it be nice to be able to check it right when we turn it on to see if it's going to burn, and then be able to turn it off if we see high amperage or something? Wouldn't that be nice? Okay, so let's do that. If I knew that my VA rating was 40 and my transformer output voltage was 24, what would be the amp draw at maximum for that transformer? 40 divided by 24 is 1.66. So if you changed out that transformer and you put your amp meter on the common or the red side of that transformer and you flipped it on and you saw 2 amps on there, what are you going to do? Turn it off, because otherwise you're going to let the smoke out. And if you let the smoke out, it don't work anymore. Is that right? So that's that good factory smoke. You can't let that out. So that would mean that I'm running more current. That would mean that I might have too many loads, or I have a short in there. Is that right? Something's causing the current to increase. Is that making sense? How good is this piece of information? Good. So you saw that you had everything was okay, but somebody had added a bunch of those zone dampers, right? You know now you have too many loads in that circuit. That's what's going to cause it to go out. Is that right? You measured 2 amps on there. If you measured 2 amps, is this 40 VA transformer going to work? So what would be the next? What do? We always just throw in a bigger one and then see if that one smokes, and we throw in another bigger one and see if that one smokes. Is that right? What if I put in a 50 VA transformer? 50 divided by 24. 2.08. You're drawing 2 amps now. You're going to be safe with the 50, or what are you going to do? Go up to a 60. 60 divided by 24. 2.5 amps. Your power producing device, your transformer can produce 2.5 amps. Does that make sense? How important is that? It's Ohm's law. You said, I don't ever use Ohm's law in my business. Can you? Absolutely you can. Absolutely you can. Good. Well, that's kind of a neat trick, something that we can work with out there. So what would happen instead of having 240, what if I had a tap right here coming off of that? I would not use 10 to 1 anymore. It would be now maybe 20 to 1. Is that right? If I tapped it off there, that might be that 208 volt tap that I have on that transformer. So we're not using that part of the transformer anymore. Is it still hot? If I applied power, if I applied voltage here to go to here, would that voltage still come out this side? What do I need to do with that? Just tie it off or just cut it off or what? I need to wire nut it off because I still have voltage coming out of there. Is that right? Good. So I do need to wire that off. I can't just tie them all together, can I? No, let's not do that. All right, good. All right. Yeah, let some smoke out. Yeah. Okay. Let's look in motors a little bit. I think motors are going to be something that we need to pay attention to a little bit. We have induction motors is typically what we're going to be dealing with out there in the industry. We're going to look at the operating characteristics, types of induction motors, shaded pole, permanent split capacitor motors, CSCR motors, 3-phase motors, constant airflow and constant torque motors. So, this is a shaded pole motor. It's got 2 wires that come into it, one in, one back out again. But you'll see on that motor that it's going to have these little pieces of copper on the pole of that motor. That's going to give it direction. It's a shaded pole motor. It does not have a lot of starting torque to it. It's very... You remember the fans that Grandma had next to her chair in the living room? She had that fan and you'd stick that pencil in there and stop the fan from going around. You guys remember that? Yeah, it kind of stopped. It didn't have a lot of starting torque. We could stop that. It was a shaded pole motor. There was no capacitor to it. This is what we're going to use on our inducer fan motors, attic ventilator motors. All of those are going to use some sort of a shaded pole motor on that. No capacitor to it, just voltage in, voltage out, And if you're going to change the direction on a shaded pole motor, you would take the stator out, flip it around, and shove it right back in again. Because the only thing that gives it direction is the poles themselves, the shaded poles. Good? Good. Shaded poles. Very efficient on the industry, so you see very few of these being used for any type of blower motor anymore. What you do see a lot of is the PSC motors that are out there. PSC motors have become the workhorse of the industry. We're seeing a lot of that. Most of your compressors are some sort of a PSC motor as well. You'll see that you have the line 1 coming into the run winding and back to L2, and then line 1 coming into your run capacitor going to the start winding. Run capacitor is in series with the start winding. Run capacitor in series with the start winding. So when the run capacitor is energized, it will help provide juice to that start winding and help make it operate efficiently. So what happens is we have different poles in the motor. If you'll look inside of a motor, you'll see that it's wrapped in different loops around in there. The more poles you have, the less speed that motor is going to have. But if you pull it out, you'll be able to see what the speed of that motor actually is. A 2-pole motor is going to electrically charge north and south every 60 cycles. 60 cycles per second means it's going to have a 3,600 RPM. If I have a 4-pole motor, it's going to shift from here to here, not all the way around. So it's only going to go halfway before it goes to the next one. So that RPM is now going to drop down to 1,800 RPM. A 6-pole motor, it's only going to move this far each cycle of that frequency. When I do that, now I'm down to about a 1,200 RPM motor. 8-pole motor, we would see down to about 900 RPMs. Now that's theoretical. Basically it's saying in theory that's how fast it was going to go. Actual, what happens is there's something called slip or drag. It's going to not really make that 1,200 RPMs every time it goes around. What it'll do is now drop down to about 1075. An 8-pole motor is about 825. So when you guys are seeing 6-pole motors out there, if you open up the end of it and see 6 poles, you know it's a 1075 motor. If you open up the back of it and you see 8 poles in there, you know it's an 825 motor. Easy enough? Good. It helps you on those jobs. The wiring schematic is always on there. It never burns off. Is that right? So you know what's going on that motor all the time. You know exactly what kind of motor it is. So sometimes you may need to pop off the end of it to see whether it's a 875 or a 1075 motor. Cool? All right. Well, that'll do it for you. Pulleys. Good guys that get a little messed up on pulleys. If I'm changing the drive pulley, this is the drive pulley that's on the motor itself. If I make the pulley larger, for every 1 rotation of that motor, it's going to turn the blower wheel more than if I had a smaller drive pulley. Is that right? Does it change the speed of the motor? Does it change the speed of the motor when I change the speed, the size of this? The motor is going to be the same, is that right? It's going to be a 1,200 RPM motor or a 1,700 RPM motor. By changing the drive pulley from a small drive pulley to a larger drive pulley, 1 rotation is going to change the output of that fan. Is that right? Is it going to change the CFM? Yes. Is it going to change the RPM of that motor? RPM is going to be the same. Is everybody getting that? That's the kind of question they may ask on a NATE exam where you're going to have to stop and think that one through. What happens when I change that drive pulley? Does it change the CFM? Yes. Does it change the RPM? RPM of what? RPM of the drive pulley, the RPM of the motor? Yes, it does. Yes, it does. Cool? All right. Motor ratings. There's LRA, which is a locked rotor amperage. Do we ever see LRA on our motors? Every time that that motor starts up, it starts up from dead stop. Is that right? If it starts up from a dead stop, you see the amperage jump up. Is that right? And then back down? That's because it started off at lock rotor amperage. So you'll see LRA on that every time. We don't want to see lock rotor amperage when it's trying to run and it's not. FLA and RLA, full load amperage and rated load amperage. A long time ago, and if you heard some of the old guys talk, they'll talk to you and they'll say that that's running load amperage. And the running load amperage was different back in the day, but sometime back in the 60s that changed and turned into rated load amperage. Rated load means that if I have a compressor and I'm drawing 240 volts on a 95-degree day at these pressures, this is the amperage that I'm going to get. Does that make sense? That way the different motor compressor manufacturers can all rate their compressors at the same rating where they can get the output for that compressor. Does that make sense to you guys? Because otherwise I could just change the voltages and get my amperages to drop down very easily just by changing the voltages. So rated load amperage, can I operate outside of rated load amperage? If it's rated at 95 degrees at 240 volts, can my compressor sometimes operate higher than rated load amperage? Quite possible you could be outside of rated load amperage. Doesn't necessarily mean that the compressor is bad. It does mean that it's operating outside of rated load or what the rating was set up for. Everybody good with that? Good. CW, CCW, clockwise and counterclockwise. I thought everybody would understand that, but there's no clocks anymore. When you don't have digital clocks, you got to explain that. So here's the deal. If I'm looking at it and it's turning this way, it's clockwise, is that right? The clock goes this way. Counterclockwise would be this way. I need to pay attention to, is it clockwise from the lead end of the motor, where the leads come out, or is it clockwise from the shaft end of the motor? Some manufacturers still rate shaft ends. Most of them rate at the lead end of a motor. Because if I'm looking at the lead end of a motor and it's turning this way, it is. If I'm looking at the shaft end of that motor and it's turning that way, it's. Does that make sense? Good. Most of your motors are rated from the lead end. All of your blower wheels are rated from the hub side. So I might have a clockwise motor, but my blower wheel will be counterclockwise. Does that make sense to you guys? Kind of nice to know? Yeah. Yeah, nice to know. All right. So you'll get that information right here. What is this? Counterclockwise lead end. So they're telling you right there on that motor. And typically that's where we're going to be seeing those set up. Look, it's got a capacitor, 7.5, 370 volts AC. There's my amperage. If you're questioning horsepower between motors, your amperage is probably going to be your best bet on motors. Some of your OEM motors are going to bump up the amperage to drop the horsepower, so you have to buy their OEM motor. If you're in doubt on the horsepower, check your amperage. That's going to be your best bet. Okay. Oiling or not oiling, we used to oil all these motors. We'd have end caps on the end of it. We'd oil all these motors. You were supposed to put 2 or 3 drops a year, which meant the technicians put 2 or 3 squeezes in every year, which means we over-oiled, which means we just drained all the oil out, which means we killed a bunch of motors. They said, well, you guys can't oil them up, so we're going to take that away from you, so you guys don't oil motors anymore. All right, that's how it works. Motor protection. There's 2 types of motor protection. Typically what you're going to see is a thermal overload. It's going to be that switch that opens up and shuts off. There is something called impedance protection, and that's typically going to be on your shaded pole motors. The impedance protection means it's going to impede the voltage. That means it's going to be what? Slowing down the voltage. Yes, resistance. So when it does that, if I can slow that voltage down or stop the voltage, what's going to happen to that motor? There it is. There it is. So typically on your shaded pole motors, you can have impedance protection, and on all your other motors you're going to see out there, you typically have thermal overloads. How does the motor work? PSC motors require 2 windings with current that gets offset during the timing to provide starting torque for the rotor. I like to think of it this way. We had that shaded pole motor, and it's like having a bicycle with 1 pedal. You can pedal it, but as soon as you start to go uphill, yeah, it just doesn't work very well. When I add a capacitor to that run capacitor, it throws another pedal into the mix. Your voltage and your current just get shifted out of phase just enough where this one's hitting at a high point when this was starting to drop down. So it's kind of like adding that second pedal in there. It's a 2-phase motor. Does that make sense? Good. So now when I'm going uphill, it works out a little bit better. Does that make sense? Good. So as the resistance increases, having a capacitor in the circuit helps out. When alternating current flows through a motor winding, 3 things can occur: resistance, inductance, and capacitance. Alternating current produces rotating magnetic fields. Magnetic rotation starts the motor, and let's figure out how that capacitor fits in. Here's our run capacitor. It's liquid filled. It's liquid filled with oil to keep it cool. What happened to capacitors over the last few years? Yeah, they started blowing up everywhere. Is that right? What do you think they took out of those capacitors? Oil. Once they started reducing the amount of oil that was in those capacitors, down in the deep south, we started seeing them explode everywhere. Is that right? Absolutely. Typically, they're 370 volts or 440 volts. That is the voltage storage capability of that capacitor. It can hold up to 370, or it can hold up to 440 volts. It can store whatever. If you had a choice, put in the 440, because now it can store up to 440 volts. Is that right? I couldn't step down and say, okay, well, I only needed to store 373 volts, so I'm going to go with a 370. It's not going to be large enough, okay? You can always go up. Typically, we're 3 to 80 microfarads. You know what a microfarad is? It's a little bitty farad. It's a microfarad. Quit that. Wired in series with the start winding of a PSC motor. It's wired in the start winding of that motor. It gives the motor direction. It tells it this is the way you have to go. Ever disconnected the run capacitor? What does the motor do? Right? Doesn't go in any direction. You know why it hums? Because it doesn't know the words. Quit it. Y'all stop that. All right. It adds starting torque and running efficiency. Start to think of a run capacitor like this. Where's my guy? Here's my guy. Okay, you're gonna be my guy today because you're one of the least girthy guys in the room. So you're gonna be my run capacitor. Okay. So being my run capacitor, have you ever tried to push start a truck? See, I love it in the Deep South because I always get an answer, yeah, I push started a truck before. It's easy. Okay, so if you're push starting a truck and you have the least girthy guy around here, he's your run capacitor. Is he going to give that truck direction? Yes? So he's going to give that truck direction. And once you pop the clutch, because you're the smart one, right? You're going to be in the truck popping the clutch. So once you pop the clutch, that truck's going to go, boom, don't. Is that right? He's going to stay in the circuit to help ease that motor and keep it running efficiently. Does that make sense? He's going to stay in that circuit. So he's going to be our run capacitor. He gives it direction, and he helps with that starting torque and running efficiency. Everybody good with that so far? Good. We're going to add something in that mix in a little bit. So there's my run capacitor. It's in series with my start winding. Is that right? Good. Well, what happens when the motor starts running? What winding am I running off of when that motor starts running? Run winding. So it's running off of my run winding. What's my start winding doing?
Chilling, kind of hanging out.
It's chilling. Is there voltage going through there? Touch it.
Yeah.
Is there voltage going through there? Oh, absolutely there's voltage going through there. Now here's the deal. I talked to you about this. I said, hey, there's 3 ways that we can produce voltage. Heat, chemical, and magnetism. Okay. And I said magnetism is if I had like this rotating magnet inside a coil of wire. Is that right? What is that? Coil of wire, and do I have a rotating magnet in there? So what did that start winding just become? A generator? It's a generator. It is a generator. And it is generating something called back EMF. Back electromotive force. What? It's generating that voltage and it's running back into that capacitor. And that capacitor was rated at either 370 or 440. So it can store 370 or up to 440 volts in that capacitor. To start up, what's the first thing that start winding sees? Boom! Huh? What just happened to my little capacitor buddy? He ate his spinach. He's Popeye. He just ate his spinach for that millisecond to be able to throw that high voltage to that start winding to be able to get that direction and that starting torque to make it happen. Is everybody good with that? Sir?
Order your fingertip.
Order your fingertip if I touched it, right? Yeah. So, what kind of voltage do I see on this? More than 240, absolutely. That's what we need to know. It is generated back EMF and it's more than 240 volts. That's exactly what we need to know. Okay, so how do we measure a run capacitor? Well, we break out our handy-dandy capacitor checker, is that right? And what kind of voltage do we have on our handy-dandy capacitor checker? What kind of battery you stick in there? 9 volts, so we have about 9 volts of power that we're checking with, is that right? So, isn't that different from that back EMF that we have here? Yeah, so maybe it's going to break down under a load, or maybe it's going to work. We're going to try it out. Capacitor checker is a good way for us to start, but you got to shut down the entire system to be able to do that. So, what we're going to do first is turn off the power, right? Shut off the voltage. Make sure that that's off, because if you start putting your paws in there, you're going to get lit up. Next thing you're going to do is disconnect the capacitor. When you disconnect it, you like that? I did that. Good, huh? You like that? I like that. Okay. So I moved that over there. The next thing you want to do is discharge the capacitor. 10,000 ohm resistor or screwdriver. Okay, is what we need to do to discharge that capacitor. We can't use screwdrivers too much anymore, because if you use screwdrivers in them, a lot of them are fused on the inside. And if I use a screwdriver across it, what happens to the amperage? Amperage goes up. If amperage goes up, the fuse may go. Is that right? So it might have been good prior to you putting the screwdriver across it, but now it's not. Does that make sense? Good. So discharge it with a 10,000 ohm resistor. All right. So when you do that, you're going to measure the capacitance. You're going to put it on capacitance. You're going to put it down there, and it says 5.7 microfarads. How good is it? Good, right?
Yes, sir.
Let's see. It says plus or minus 10%. Here's the math part. 5 microfarads plus or minus 10%. So that means 4.5 on the low end, 5.5 on the high end. And we measured 5.7. It's not good anymore, is it? Good. So we're going to need to be able to explain to that customer that it's out of tolerance. Does that make sense? It's not bad. It's out of tolerance. What we did when we did this is, remember our pedals on our bicycle? We had one here and one here. Is that right? What you did when you throw your capacitor out of tolerance is you move that bottom pedal to here. It's not here anymore where it's doing this. It's here now where you're kind of doing this. It's operating, but it's not operating efficiently anymore. Does that make sense to you? All you did is take that bottom pedal and you either moved it here or you moved it here. You didn't get it right where it needs to be. And now it's just going to operate. What's that going to do to the system over the big picture? It's going to take it out, yes? Is that making sense? But you need to understand what it says. It said it was 5 microfarads plus or minus 10%. If I just plug that into my calculator, 5 times 10%, it's going to tell me that that's 0.5 is my tolerance. You go above it. What's the next technician behind you going to say if he measured it? It's okay, is that right? Because you guys just told me it was okay. I need you guys to be smart enough to be able to explain that to a customer, that it's not bad, it's just out of tolerance, and it's causing your bicycle to run a lot harder. Everybody good? Sweets. All right, so we have that 5.7. Did you know that if you took 2 capacitors and put them in parallel, that they add up? We've seen that. If I took a 5 microfarad capacitor and put it in parallel with a 7.5, it turns it into a 12.5 capacitor. That's really nice if I have a 40 microfarad capacitor and all I have on the truck is 2 20s or a 10 and a 30. I can put those in parallel and make that happen. Did you also know that if you needed a 3 microfarad, you probably don't have that on your truck, is that right? You have a 3 microfarad on your truck? Nah, probably not. You have a 5 and a 7.5? If you have a 5 and a 7.5, you have a 3 on your truck. If I take a 5 and a 7.5 and wire them in series, it becomes less than the least. It becomes a smaller resistance or a smaller capacitance when I wired them in series. Remember resistors in parallel drop down in resistance? Capacitors in series drop down in capacitance. 5 microfarads times 7 is 35 and a half. That 5 and 12 and a half is 3 microfarads. I want you to try that when you get home today. I want you to wire them in parallel, and they should be 12 and a half. Then I want you to wire them in series, and you're going to see that they turn into 3. So what did you just do to the stocking capability inside your truck? Are you making sense to you? Good. Every time you leave that job site, it costs you $100. Every time it costs $100 on your truck. What do you think those global turbo capacitors are? They're either wiring them in parallel or wiring them in series in there. They've just given you one capacitor to do a whole bunch of stuff for you. Does that make sense to you? Cool. I have guys all the time saying, well, yeah, Rick, I'd put that in there and I'd leave that in there all day long like that, but I don't know if I'd leave it in there like that. Well, why? Because you use one less piece of wire? What was the biggest problem with all of our capacitors out there during those last few years? What was the one thing you guys told me the biggest problem was? They didn't have enough oil. What did I just do to the oil in this? I doubled the oil, absolutely. Is this a lot less than the $100 that it would take for you guys to run to the jobs, to Coburns and pick up another capacitor than what you have right here on your truck already? What is it that you're going to do? Come on, tell me the truth. If you had a 3 microfarad capacitor that was out on that job site, what would you have put in? Come on, tell the truth. You'd have put it to 5 and you'd have walked away all day long, is that right? What just happened to that bottom pedal? We just shifted that bottom pedal, didn't we? Absolutely. Did you have a 7.5 on your truck that whole time? Yeah, sure did. Could we have made a 3? Absolutely. You guys have that capability. But that's math. And who's going to do math? Oh, wait a second. If you go to the Coburns App, and you put capacitor 1, capacitor 2 in there, if they're in parallel, that 5 and that 7.5 turns into a 12.5. But if you run them in series, that 5 and that 7.5 turn into a 3. What? It does the math for you? How cool is that? What? You liking that? Huh? Who loves you now? Come on. Huh? Who loves you? There it is. There it is. So Jody and I have been working very hard. Jody's been giving input as well. But this is good information we think that you guys can utilize out there, and the app is there for you for free. Fair enough? Cool. All right. All right. So dual capacitors. Dual capacitor. Here's how it's wired. You have a common, comes in here. And then your F is for your fan, and the H is for hermetic, which is compressor, right? It's a hermetic compressor. So you have your C for. Why don't you think they put compressor here? C. Oh, because we used the common already for that one, so we couldn't put compressor. We had to put hermetic. So it's common, fan, common, hermetic. It's just two capacitors built into one unit right there. They're still liquid filled. They're still typically 3040 to 370, 440, two capacitors in one, wired in series with the start winding for the PSC and the compressor. It's wired in series for the fan motor start winding, and it's wired in series for the compressor start winding. It adds starting torque and running efficiency for both the fan and the compressor. Capacitance under a load. Well, you can check your capacitance on that unit while it's running. So instead of having to turn off the entire system, ohm out that, put the capacitor checker on that capacitor, you can check it while it's running. The formula says 2650 times amps divided by volts. What they don't do is tell you what amps of and what volts of. So here I added this in. 2650 times the amps of the start winding. So you get the amperage of the start winding, and then you divide it by the voltage measured across the capacitor. Everybody good with that? All right, so let's do that. What we're going to do, take the amp reading on the start winding. We're going to take the voltage readings across the terminals of the C and Herm on our capacitor. The voltage reading is going to be higher than line voltage. Is that right? Because that's that back EMF that we're measuring right there. So example, if I had 227 volts on my T1 and my T2 of my contactor, I had 3 amps measured on the start winding, I might see 317 volts across the terminals of the run capacitor, because that's generated voltage going back there. That's called that back EMF. 370 or 440 on the capacitor. A 440 capacitor can always be used to replace a 370 because that's just the storage capability of that capacitor. So we take the 2650, that's a constant, it doesn't change, times my amperage of that start winding, divided by that voltage that I measured across there. So 2650 times 3 is 7950. 7950 divided by my 350, I'm operating right now while that unit is running 25.4 microfarad. If it's a 25 microfarad capacitor plus or minus 10%, how am I doing? If it's a 30 microfarad capacitor, how am I doing? Okay. Does that make sense? Good. But it's math. Nobody likes math. Man. What if on that app we gave you amps of the start winding, amps of the run winding, and gave you the operating capacitance? How cool would that be?
That'd be too much.
Man, that would be awesome, huh? How cool would that be for you guys out there in the field to be able to make that happen? You liking that? Jody's good. Jody's good at what he does. I'm telling you, he's the man. So we have it there for you guys. It's under operating run capacitance. All you have to do is download the app, go to Coburns.com, and you'll have it there as well. It's there for you. Cool? Like it? Yeah, I liked it too. Jody and I were thinking about this and going, man, if I'd have had this when I was younger out there in the field, it would have sure made my life a lot easier. So there it is. We've tried to make that. Oh, what is this? What kind of capacitor is that? Start capacitor. That's different from what we had a while ago. We had him out there push starting that car. This is a start capacitor. It's typically 250 or 300 volt, typically 88 to 300 microfarads. What happened to our microfarads? Big microfarads. It's wired in parallel with the run capacitor. When I take two capacitors and wire them in parallel, what happens to that? They add together, right? When they're in parallel, right? Parallel, they add. Series, they lose, right? Okay, so start capacitor and the run capacitor, what's going to happen now to that starting torque? Yeah, it's going to go way up. At substantial starting torque. Stays in the circuit for less than 3 seconds. It works in conjunction with a potential start relay. So let's think about that. You got him, and he's your run capacitor, is that right? It's a truck. It's got low tires, and you're on a gravel road. How's he going to do? He ain't going to do good. You better get a start capacitor to help him out. Is that right? Yeah? And you want that start capacitor right in parallel with him, right? Good. So that's going to be good. I'm a girthy start capacitor. So I got a lot of capacitance to help him get that thing started, and he's going to give it direction. Is that right? And we're working in parallel, not series. Is that right? We're going to work in parallel, right? So quit that. So we got that going. So we're going to get that parallel working going on. But he's young. He's strong. He's young. He can stay in that circuit after we get that thing going in that direction. He can stay there, and it's going to and he'll stay in that circuit. If you keep me in that circuit any longer than 3 to 5 seconds, what do you think is going to happen to me as we start getting down that road? I'm going to explode. I promise you that. It's going to get ugly. There's going to be smoke let out everywhere. So I'm going to go down that just long enough to get it up to speed, and then it's yours. Does that make sense? And how do I come out of the circuit? With that potential start relay. That potential start relay is going to take me out of the circuit so that you can take over and make it run. Does that work for you? Cool. So this is how it's wired. Is it wired in parallel with the run capacitor? Yes? Runs right through a switch. Is that right? When that thing starts running, it starts generating what? Back EMF to that capacitor. Is that right? What's connected to that capacitor? Oh, that coil. So that back EMF is going to that coil. Is that right? If I had a 24 volt contactor and I only put 15 volts to it, would that contactor pull in? It waits till it gets real close to 24 volts. Is that right? Good. So if I had a potential start relay that I had a coil of, I don't know, 313 volts, that back EMF would have to get real close to 313 volts, and when it did, what's it going to do to that switch? So when it starts generating just the right amount of potential back EMF, it's going to open up that potential relay and take me out of the circuit. If I just start sticking generic start kits in there, I might come out of the circuit a little too soon, or I might come out of the circuit a little too late. But either way, it's going to be detrimental to me. Is that right? And maybe your compressor? Possibly. So understand what you're doing. We all stick a lot of generic parts in there, and that's okay, but as long as you understand what you're risking. Fair? Cool. All right. Everybody have a better understanding of capacitors? Good. Good, good, good. All right. So here's a circuit with the outdoor fan motor and the compressor. And you'll notice your run capacitor in each of them. Two separate capacitors. Comes from the line through the capacitor to the start winding. Comes from the line through the capacitor to the start winding. That would be two separate capacitors. This is a dual capacitor. Comes from the line to the common side of the dual run capacitor, then it goes to the fan, and it goes to the compressor. Anything wrong with that? Can I take a dual out and put two singles in? Can I take two singles out and put a dual in? Absolutely can. Is everybody okay with that? Good. Three-phase motors in there. Remember what I said about that bicycle? It had two different phases, pushing on that. What do you think is going to happen to the starting torque if I threw another phase in there?
What would you use to turn the pedal?
If I had a third phase that I could push that pedal, it would make everything operate a lot more efficiently, a lot more smooth. Is that making sense? Good. So our starting torque on our three-phase is going to be very, very high. Can we have a three-phase compressor with a single-phase fan motor? Let's take a look and see. This would be my line 1, is that correct? Coming in through my contactor into my compressor. My line 2 coming in through my contactor to my compressor, and my line 3 coming in through my contactor to my compressor. Is everybody seeing that? That would be a three-phase unit. Notice on here that that blower has a capacitor. If it has a capacitor, it's telling me right off the bat that I have single phase to that motor. I have line 1 going to my motor, and I have line 2 going to my motor. So I would have a single phase blower with a three-phase compressor. Is everybody seeing that? I'm just using, and in this case, my condenser fan motor is the same thing, okay? Or my blower motor and my condenser fan motor are the same. Good? Now notice this right here on the transformer. Here's that piece again. You got your 24 volts, your common, your 208 is tapped off a little bit sooner than that 240 volt transformer. So what if I had my 240 volt transformer and I applied 208 volts to it? What would my output voltage be? If this is a 10-to-1 ratio, because it's 240 to 24, and I applied 208 volts to that 240, what's going to be my output? About 20.8 volts, is that right? Good. So understanding what voltage you have and setting up your transformer to help that out, because you just told me that contactor might not pull in if I didn't get the right voltage to it. And if I'm only putting out 20 volts on that, it may not be pulling in. Does that work for you guys? Cool. All right. Three-phase motors. You have 3 separate windings. All of them are going to have the same resistance. And typically you're going to have one overload right there in the middle. So if the one overload opens, all 3 windings are going to be open. Does everybody get that? All right. Changing the line wiring to any 2 of the 3 is going to change the direction of that motor. So if I change line 1 to line 2, line 2 to line 3, line 1 to line 3, if I change any 2 of those wires around, I'm going to change the direction of the motor. That's fine as long as I'm not dealing with a scroll compressor. If the scroll compressor gets changed, it's going to start running backwards. And what does that sound like?
Like nails.
It sounds like nails. It sounds like, yes, sounds like rocks inside that compressor. It sounds bad. The other thing I need you to understand, if you're going to do it on large reciprocating compressors, make sure that the oil pump is turning in the right direction as well, because sometimes you'll run that oil pump backwards as well. So just be aware of that. So you don't want to just start flipping it around until you've checked that as well. All right, there's 3-phase delta, 3-phase Y. Not a lot that I can tell you about that other than they can also be dual voltage. I can either have 440 volts, I can have 230 volts to that. It's just going to be how you wire it up. T6, L1, T1, you'll wire that up separately on each one of them, and every one of those motors is going to be a little bit different. So let's talk about variable speed motors just a touch, because I think there's enough in variable speed motors that I have to let you know what's coming in the near future with these things. They're used for indoor blowers to provide infinite control of the speed and the strength of the motor for proper airflow. The OEM manufacturer stuff is critical. Every manufacturer of these motors comes from probably less than 4 manufacturers of motors, and each one of them is going to specify their input information differently. So you can't just take one Regal Beloit motor and replace it with another one, because the software is different from one manufacturer to the other. So the OEM stuff is critical. Set the dip switches. They don't come from the factory with the dip switches set. How many calls do you get, Jody, every week on, well, I left it that way because that's how it came from the factory? Yeah? Lot, absolutely. Variable speed motors are designed to overcome some airflow problems, but can't correct severe problems. Don't say, oh well, I've got a crappy ductwork system, so I'm going to put a variable speed motor on it and make it work. It'll just destroy that motor. There's X13 motors, they're called constant torque motors, and there's variable speed, which is true variable speed. They're called constant airflow motors. Understand that there's a difference, okay? Constant torque and constant airflow. If you're looking for a lot more information, go to the Dealer Tool Belt app. It's a great app, and there's a ton of good information for you guys there. I want you to be aware of that. So, getting into that, they were introduced in 1986 in a time there was 100% PSC motors in this industry. It's used for the indoor blower to provide infinite control of speed and strength. Tools needed: you'll need a voltmeter, AC and DC. You'll need a broad ocean motor tester, or a Tech Inspect motor tester for the Regal Beloit motors. They can't be interchanged back and forth. So if you're dealing with some of the old Nordyne stuff, you'll need the broad ocean motor tester. If you're dealing with just about everybody else's stuff, you'll need a Tech Inspect. What are they? Less than $100, I think, for each one of those tools. Get them. Get them. Variable speed motors are designed to overcome some airflow problems, but not severe ones. Here's what's happening with ECM motors. You say, oh, well, Rick, I'm really not big into that. I like a PSC motor. I'm good there. That's fine. 86, we were 100% PSC motors. 87, the OEM started coming out with a constant airflow motor. It was very expensive. We started seeing problems with moisture in those things. We had a lot of failures. They were very expensive to change out. 2005, the industry shifted to a higher SEER, 85% PSC, 15% ECM. So at that time, we were still 85% PSC motors and 15% ECM motors. 2006, we hit the 13 SEER minimum, caused 45% PSC motors, 40% ECM constant torque motors, and 15% constant airflow. So that's when that X13 came into play. In July 1st of 2019, FER is coming into play, and it's expected that there'll be minimum PSC motors left out there. We'll still see them in some of our air handlers, but on all your gas furnaces, you'll see ECM motors on all of those. We're expected it to change to from 80% PSC, minimal PSCs, 80% ECMs, and 20% CA motors. We'll see just about the whole industry shift over to variable speed motors, that constant torque motor. So if you didn't like them before, understand that's going to be your future. Yeah. So just be aware of it. So let's take away some of the magic on some of these things so that you guys get it. ECM motors are a combination of a control module and the motor itself. There's two inputs. You'll have the communication voltage and the line voltage. That's basically it. Communication and line voltage. The motor controller module, the motor module, you see that they just open up, separate. There it is. I like this graphic because it kind of really shows what happens. You take 120 or 240 volts in, it goes to a control, converts that AC power to a DC power. Once you convert that over, now we're going to convert that DC into a three-phase. So instead of it doing a sine wave like this, it's DC. It's on, off, and it just changes that sine wave to a direct current, but it's a pulsating, if you will, pulsating DC current. So we're going to change that AC current into a three-phase pulsating DC current. The communication part of this is going to say, I need that voltage to be 3 volts, 5 volts, 7 volts, whatever it is. That's the communication part. It's going to tell you the higher the voltage, the faster it's going to spin. Does that make sense? Good. So coming back out of it, you end up with a 3-phase motor at the other end. So knowing that I have a 3-phase motor, I know that the windings should all have basically the same resistance. Does that make sense? Good. So it's going to be easy for us to check this out. Constant airflow motors, these are those ECM motors with the variable speed, true motors. They're going to either be a 16-pin or a 4-pin typically on the Gentech side of that deal, and it's going to have 24-volt AC, DC, pulse width modulation. Again, that's where we're going to come back to the manufacturer specific. You will always have the 5-pin plug on this side that's going to be your line voltage. It's either going to be 240 volts or 120 volts. That's going to always stay constant. What's going to cause it to run is going to be the communication that comes from the board. Good. So if you don't have voltage here, it's not going to run. Is that right? You first have to check, do I have voltage? If I have voltage there, then we can start working our way back to the board. Good. Constant airflow motors. Guys, there's the switches in here that you have to actually set. If it's a 800 to 1400 CFM motor, you have to set those. They don't come from the factory knowing what you guys are going to put it on. Does that make sense? You have to set that. You have to set your cooling airflow, your heating airflow, your trim, which says, okay, well, I don't want to have 400 CFM. I want to have 350 CFM per ton. So you're going to add your trim in there, either 10% up or 10% down. Your climate delay profile, that's going to be, do I want that system to stay running after the air conditioner shuts off? Do I want the fan to stay running? If the fan stays running when that system shuts off, is that coil still wet? It's still wet. So if the fan stays running and it's blowing across a wet coil, what did you just do to the house? Add the humidity back in there that you just took out. So when we're dealing with variable speed motors, we want what to happen on our motors in our marketplace. When that system shuts down, what do we want to do? Shut the fan off, okay? So that's where this climate delay profile comes into play. All right? So all of this says OEM manuals. All of that right there comes from the manufacturer, and it's manufacturer specific. You have to know your product or that particular product. What does Jody and I always say? RTM. Read the manual. Read the manual. You have to read the manual. We can't just do what we've always done in the past. We have to read the manual now. It's specific to that particular motor. So, constant torque. Again, we're going to have one set that's going to be our high voltage, and then the other one's going to be our 24-volt outputs on the bottom side. It's real easy. Here's my line voltage coming in, and then I got my 24-volt common, and then I have my inputs to that deal as well. So it's going to be 1 speed, 2 speeds, 3 speeds, 4 speeds. How many speeds it's going to be? You can always check first, do I have voltage applied? If you have voltage applied, then you start working backwards. Do I have the input voltages there? This is what you're going to see most of. The X13, that constant torque motor, is going to be the biggest percentage of the motors you guys are going to see. It's 110 or 100 or 240 volt input, and you're going to have a 24 volt signal to make it come on. All right? So, there it is. It's that constant torque. He's got 240 volts or he's got 120 volts. What communicating voltage is he going to have on that? It's going to be a 24 volt probably, right? Where's it going to go? Which ones are you going to check? You have to do what? Read the full manual, you know. You have to read the full manual, because otherwise, oh, I know what you guys were thinking. Oh, quit that. Yeah. Yeah, that's it. We're going to have to read the manual. We don't know what the inputs are being, because everyone is going to be different. Does that make sense? Good. I know we don't like to read the manuals, but that's what we're going to have to do going forward. Good? Especially the full manual? Yeah, I got you. TechMate, here's that motor tester. If I just pull the communicating part out, put the TechMate into that, connected that to 24 volts and pressed on, and the motor runs, what's good?
The motor's builder.
That's good. Does that make sense? Something over here may be not sending us that signal. Does that make sense? Cool. All right. How easy is that? What do you need? And you need two different ones. You need one for the broad ocean, and you need one for the Gentag motors. Okay, so just know. And if you want to get the one that's out there, and there is another brand out there, just understand it's got 175 wires to it. And if you want to play with that, that's yours. I'm telling you, get two separate ones, and you'll be a whole lot better off. Fair enough? Okay. All right. If the ECM motor operates with the Tech Inspect motor, diagnose the board, right? We're going to go back to the board, and that's going to be going back to that OEM stuff. If it doesn't, we're going to need to find out, is it the control module or is it the motor itself? So what we're going to do is we're going to separate that. But before we do that, it's important for that power to be shut off for 5 minutes. If you don't discharge that motor for 5 minutes, those capacitors will hold a charge. And unless you have your helper doing this for you, it's going to light you up. But it's really kind of fun to watch him do it, okay? Okay, so separate it out, and you're going to ohm, because all we have is 3 wires, right? We're going to just ohm between the 3 of them. L1 to L2, L2 to L3, L1 to L3. The reading should be less than 20 ohms, and should be less than 10% deviation between them. So if I had 5.1, 5.2, and 5.3, everything's good. If I start getting 5.5, that's 10% deviation. Is that right? Good. So in this particular case, 5.1, 5.2, the motor's good. What's the problem? Module itself. Everybody good with that?
Isn't that what always goes bad?
Sir?
Isn't that what always goes bad?
Yes. Yeah. There's very few times that we're seeing the motor go bad. Okay? All right. So here's a graph that Jody and I put together. I think this is really kind of cool. It's something I want you to pay attention to, because this is the thought process that's a little goofy. If I'm dealing with a PSC motor, when you're dealing with a PSC motor, as the static goes up, CFM goes down. So as the resistance inside that ductwork goes up, what happens to the CFM? It drops off. All right. Constant torque motors, that's that X13 motor. As the static goes up, the CFM goes down. Static goes up, CFM down. As static goes up, the amperage goes up. Okay. So wait a second. When I put these X13s on that bad duct system, what's happening to the CFM? Goes down. What happened to the amperage? The amperage just went up. Now I'm going to burn up the motor. All right? On a variable speed application, on a true variable speed motor, its job is to get that airflow out there. Whatever airflow you're asking for, its job is to get that airflow out there. So if I put that true variable speed motor on that bad duct system, what's going to happen to the airflow? It's going to get it, right? It's going to make that thing happen to a point. I mean, up to about 0.8, it's going to get it out there. What's going to happen to the amperage on that motor? It's going to get you that airflow or die trying. Does that make sense? So when you start playing with some of these variable speed motors, they may try and get you that airflow that you're looking for, but in both cases, They're going to kill that motor. Does that make sense? What we're going to do is we're going to shift our world now. We're going to go back to something a little more practical, something you guys see on a regular basis. Now, I wrote this class for a technician who does not have any idea about anything, so we're going to go right to the beginning and say R is going to be your 24-volt power. That's going to be your voltage applied. G is going to be your indoor blower motor circuit. Your W is going to be your heating control circuit. Y is going to be your cooling circuit. And your C is going to be the other side of your potential. That's going to be your neutral potential, if you will. That'll be the 24-volt common. So if we have our thermostat, our gas furnace, and our condenser, when I have 24-volt voltage going to my white, it's going to send that to my gas furnace and cause my furnace to come on. If I send that R to my G, it's going to turn on my blower motor. If I send my R to my Y, it's going to run out to my condenser and come back on my common and be able to make that contactor come on. Is everybody okay with that? Nobody's lost on that part right there. All right, good. All right, so one of the ways that I like to teach technicians to get started, and sometimes when a senior tech gets lost, I tell them to do the hopscotch method. And the hopscotch method says, okay, my load is not working. Let's find out, number one, do I have source voltage? If I have source voltage, it's going to show up and say, yes, you have two different potentials on your meter. You've got 120 volt. I will take my neutral and slide it right to my load. From there, if I show that I have source voltage, I know that I have the 120 volt potential, and my neutral potential made it all the way to here. Does that make sense to you guys? Good. Then I'm going to just take it in one step at a time. Do I have voltage there? Yes. Do I have voltage there? Yes. Do I have voltage there? Yes. If I have voltage to the load and the load doesn't work, poor load. Does that make sense to you guys? Good. It's called the hopscotch method. Sometimes when you start getting lost on a job site, just go back to the basics. Step it here. All you're trying to do is get that voltage to the load. Is that right? Find out where you're losing your voltage. In this particular case, we've got voltage to the load. If you got voltage to the load and the load doesn't work, bad load. Good? All right. All right. So, voltage is across a switch. I see this all the time. What would I read across that switch right there?
Line voltage or control voltage.
But it's open.
Well, that's why you read it.
Ah. Do I see L1 potential to my meter?
Yes.
Do I see the L2 potential to my meter? Good. If I see two different potentials, what am I going to read? The line voltage. Is everybody good with that? Across a switch, am I going to see the two different potentials across that switch? I'm going to see the L1 potential to here, and I'm going to also see the L1 potential to here. If I see L1 and L1, what is my meter going to read? There. Does it mean I don't have any voltage there? So what do I read across an open switch? What do I read across a closed switch? 0. 0. Does it mean there's no voltage there? Good. Is that making sense? I know that's a tough one for some technicians to get their head around, and I just want you to see it. If you see it in a picture, sometimes that picture is going to stay in your head, so when you're out on that job site, oh, I got it. So closed switch, you're going to read 0 because I'm seeing the same potential. That's like me taking my meter and putting it just like this. Is that right? It's not going to see. I have to be on the other side of that load for me to see that second potential. Everybody good? All right. So, interpreting the voltage. No voltage at the load. If you don't have any voltage at the load, you can't say that the load is bad. You can't say that the voltage is not, the motor's not good because the voltage is not there. Something else is not allowing the voltage to get there. Full voltage to the load. The circuit feeding the load is complete. The load should be working. Voltage across the switch is probably open. 0 voltage across the switch is probably closed. Everybody good with that? Sweet. All right, so let's use our meter. what would I read across R and C if my transformer was in that gas furnace right there? 24 volts. Good. Your thermostat switch is off and the fan switch is in the auto position. Would I still read 24 volts? Absolutely. All right, let's switch it to cool. Your fan switch is in the auto position. R and C, what should I read? 24. That's where my voltage is being generated. Absolutely. So now I'm going to shift down to the W. What should I read across W and C if it's in the cooling mode and in the auto? 0 volts. Because I'm seeing nothing from the red going to the W. Is that right?
Correct.
Good. What would I see on the G? Am I going to get the fan relay to kick in on this? Good. I have to energize that G, so I would see 24 volts there. What would I see on the R and the C in the heating mode? Okay. Sure enough, there it is. All right, let's go to the W and C in heating on the auto. Should my gas valve be kicking in? Yep, should be. So I should see 24 volts. What about the G in the heating? What's going to bring on that circuit? Yeah. I could read 0 there, depending on if the fan relay is bringing a fan temperature sensor is bringing it on, or whether it's actually being brought on by the board. Absolutely. So what about the Y circuit right there? Good, I'll see 0 right there as well. All right, the thermostat is in the off position. The fan is in the on position. Fan on switch is in the on position. What should I read between G and common? 24 volts. Everybody good with this so far? Sweet, all right. Let's shift it over to the thermostat. You're in the heating mode. What should I read across R and W? If I'm in the heating mode, it's in the auto. R and W. You with me? What do I read across a closed switch? In the heating mode, is the R and W closed? R and W is closed. I should read 0 volts. Everybody okay with that? Good. All right. Let's do R and G on that heating mode. What am I going to see? 24. Absolutely, I will. Will I see the common side coming back to this side of the G? Will I see the R potential? Absolutely, I will. Absolutely. Sure. So 24 volts there. Doesn't mean that the fan's running, does it? Nope. All right. What am I going to read across the R and the Y? 24 volts. Absolutely. And if you're not getting these, I need you to play with this when you get back, because this is your weak point. And trust me, a lot of technicians, this is their weak point. And I'm doing this just to help you identify that this is a source you need some help with. Fair enough? Play with this. All right, so if we're talking about a heat pump, I just wanted you to understand what that heat pump does. There's a B and an O terminal on your thermostat. The B energizes it in heating. The O energizes it in cooling. It's easy to remember. If you use the O, there's 2 O's in cooling. O, it energizes in cooling. The B for heating. All right. So we just understand that if you have the O terminal, you know it's going to energize in the cooling mode. Everybody okay with that? Good. So what does that mean? Well, you have, when we talk about a reversing valve, it's 2 reversing valves. It's the pilot valve down here at the bottom, and the main body valve here, the slider body here. So first of all, the coil energizes this valve, the pilot valve. This is high pressure gas, and this is always the suction line. So this is always low pressure, this is always high pressure. If the valve is sitting like this, not energized, the pressure goes in here, goes up to this side and puts high pressure on this side. This low pressure gas goes here, loops through, and goes to this side. So if I put high pressure gas on this side and low pressure gas on this side, this body does. If I energize this and shift it over, that high pressure gas now goes to this side, and the low pressure gas now goes to this side, and it shifts it back. Does that make sense? So these valves are electrically initiated and pressure operated. Electrically initiated, pressure operated. So if the valve doesn't shift, it may not be anything in your electrical circuit. It may be that you just don't have enough pressure to be able to get it to shift. Does that make sense? Good. All right. When your thermostat is calling, you will receive 24 volts on your meter at common and the called for circuits. Does that make sense? When your thermostat is calling, you'll receive 24 volts on your meter at common and any one of those circuits it's calling for, whether it's calling for heat, cooling, fan. Good? You'll read 0 on your meter from red to the called for circuits, because the red is our switch, red to whatever. So you're going to read 0 across a closed switch. No voltage at the load. The circuit feeding the load is incomplete. Full voltage to the load. The circuit feeding the load is complete, so the load should be operating. Voltage across the switch means the switch is open, and 0 volts across the switch means the switch is probably closed. Everybody good with that? Good. All right. Here's where we get to play. Y'all ready? I want y'all to shout out the answers, all right? Because this is the fun part. Everybody good? This is the audience participation. Everybody ready? Okay, here's the audience participation part. Y'all ready? Yeah. Yeah, okay, here we go. All right, here is your meter. Here is a condenser. You got your compressor. You got your condenser fan motor. Everybody ready with this? All right, we're going to take our meter and we're going to plug it on here and here. What should I read? It's energized. It's ready to run. What am I going to see? Okay, there's the audience participation part of this class. Maybe I didn't get that out there. Okay, this is a condenser. Okay, compressor, contactor coil. Yes. Is the contactor operated or not? Yes, it's operated because it's pulled in. Yes? Yes. Good. All right, so it's energized. What should this be doing? Running. Okay, good. So if I put my meter across the contactor coil, what should I read? 24. There we go. Now we're kicking chicken. All right, so here we go. We're rolling. We've got it. So I'm take my meter and I'm going to put it across here and here. What should I read? Do I see my L1 potential to the red? Do I see my L2 potential to the black? Yes. What should I read? 240 volts. Is everybody good with this? Yep. Yeah, okay, all right, we're rolling. See, you guys are scaring me out there, because I got just very little people going, no, I don't know. Whatever my meter tells me, that's what I'm going to read. That's what it, all right, well, we got to find out what it's going to read before, that way we know if it's right. Everybody good? All right, okay, so, yeah, I got 240. It's the one time in your life you're going to see 240 on your meter. Here we go. Here and here. What am I going to read? Is this a load? Is this a load? Yes. See voltage to a load? Yes. Do I see the L1 potential to the R? Yes. Do I see the L2 potential to the C? Yes. What should I read? 240. What? Here we go. We kicking now. All right, here we go. You ready? Got one here and one here. What do I read?
0. Oh, it's going to be more because that's a capacitor. It's gonna
what? Talk to me. Back EMF. There we go. There's my back EMF. What should I see there?
More than 240.
More than 240. Is that right? More than 240. Excellent. Yeah, that one usually stumps everybody. I usually get 240 out of that one. Yeah, that's going to see back EMF. I'm going to read that generated voltage coming back off of that start winding right there. It might be 370, might be 390. Is that right? Sweet. Good. There it is. So it's 280 plus. Good. All right. Let's look at here and here.
That's a 0. It's the same line.
Do I see L1 to the black? Do I see L1 to the red? Yes. What am I going to read?
0.
0. That means I can touch it, right?
Absolutely.
You can, right? You can touch it, Rick. Yeah, we want to see you jump. Yeah, no, it's not going to work. Okay. Uh-oh, what's that? Oh, you guys don't have any of that around here, do you? No, not down here in Texas. All right, so we got that big old ant stuck in that contactor, and we're going to check here and here. What are we going to read? 240 volts, is that right? Sweet. How about here and here?
110 or 120.
110? 112?
114.
114?
Depends on where you're at.
Depends on where I'm at. I'm in Texas.
What is voltage?
About 122.
122. Do I see the L1 potential to the red?
Yes.
What potential do I see on the black?
Oh, L1.
So you'll end up with 0.
0. Right? It goes through.
I'm seeing L1 on the red, and I'm seeing L1 on the black. What am I going to read?
0.
Absolutely. Does that work? Good. And these are seasoned technicians. Okay? So I mean, what I'm telling you guys, I'm not trying to beat anybody up here. I'm just saying this is what we find. So when we're trying to use our meter, we need to know what our meter is going to tell us before we stick our meter on there. Is that right? Because if I got 120, that means something has got a ground on it. Does that make sense? Because I got an L1 potential and I got a ground potential somewhere. Or a neutral potential, yes? Right now, I'm just seeing 0. Does it mean I can touch it?
No.
No.
You can if you want.
You can, but I ain't gonna bite you. It's gonna bite you. All right, so that's a 0 potential. All right, how about here and here?
Well, now you get 110 or whatever. It's, yeah.
You get one leg.
Oh crap. Yeah, you know.
Good. I want you to guess, but I want you to start thinking about it too. Do I see the L2 potential to the red?
Yes.
What do I see on the black?
220 L1.
I see the L1 all the way around to the black, don't I? Yeah? Do I see the L1 potential all the way through here, all the way to here?
Yes, sir.
I see L1 here and L2 there. What do I see across an open switch? Line voltage. Is that making sense to you? Yeah. Sweet. What am I going to read here? Excellent. Excellent. Everybody learning something? Yeah. So, what is that? What? Yeah, that's that guy. Okay, that's that guy that reads everything to ground. Okay? If you're using your meter to ground on an AC circuit, I want you to see what's going to happen here. We're going to take one, wrong way. One leg, and I'm going to stick it to the L1. Everybody good? Put the other one where? On the ground, because that's how he's learned to check it. Is that right? Good. What's he going to get here? 120. Good. What's he going to get here? 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 What did it tell you? All it told you is don't touch that. Is that right? That's all it told you. It didn't tell you where the problem was, did it? No. Understand that. Understand reading across an open switch, reading across a closed switch. It's huge in your business. And don't start reading across switches with your own meter just to see, because if you're using that continuity deal, you can still have continuity and still be dropping some voltage. Does that make sense? If the contacts are dirty, is that a resistance? Is that going to produce magnetism or heat?
Magnetism.
Heat, is that right? So if we're reducing heat here, that means we got some of the voltage being dropped here, but then there's going to be some other things that are not going to see all that voltage. Does that make sense? Good, so good. Well guys, what are we going to read here? Here and here. The contactor coil is burned, is that right? So what am I going to read there? Still at 240, is that right? So what do I read here and here? 0. So what do I read here and here? 24 volts. If I have 24 volts to the load and the load doesn't work, Bad load, absolutely. Guys, I want to thank you very much for participating with us. I hope you learned something from this. If nothing else, I hope you learned what you don't know. How's that? Good? If that tells you what you don't know, then there's going to be times that you need to sit down. I gave you all of this PowerPoint so that you can, at some point in time, go back and look at it and say, that fat man said something about this. And you can go back and jog your memory. Put that on the back of the toilet. There's 15 minutes a day. You're not doing anything else, all right? Go ahead and keep that right there and make that make your world a little bit better. Thank you all very much. I hope you really enjoyed the class, and I appreciate your time. Cool? Thank you all.